So the good news is I can talk better today. The bad news is I should not, but I can talk. So I will stop the lectures more frequently to ask more questions, anybody. So we'll have more interactions because it's actually quite fun today as well. So yesterday we talked about how our sensory system recognition is really what vision is, people think, even though selection is under the tip of the iceberg. However, this is the tip of the iceberg. When we recognize, we see that we're not very good. It's not like we have a telescope looking to the sky and that star is so dim. And then you just wait to collect more light, then you will see better. We cannot wait. After 100 milliseconds, the longer you see, doesn't make any difference. So our brain is built in a very strange way. Okay, so let's start. Let's start. Okay, so let me play it.
Encoding, selection, and decoding stages, and that decoding is after the attentional selection to select only a tiny fraction of visual input information for deeper processing. So therefore, decoding must be understood in light of this attentional bottleneck. We have also argued that attentional selection is mainly by gaze shifts in humans, and this selection starts at V1, which guides gaze shifts exogenously. So therefore, the bottleneck should start at V1. Most ideas about V1 ignores the information bottleneck. We perceive only a tiny fraction of visual inputs, mainly the inputs within the attentional spotlight. This spotlight is selected mainly by a gaze shift. This visual location was in the peripheral visual field before the gaze shift. I have proposed that a saliency map is created in V1. The hotspots in this map attract gaze shifts exogenously. Therefore, peripheral V1 computes saliency to guide attention. It motivates the idea that the bottleneck starts right after V1. The bottleneck makes the information impoverished so that recognition can be ambiguous. Even in central vision, one may be uncertain, for example, whether this is a red flower or a red apple. More recently, I proposed that central vision can send a feedback to query for additional information, particularly from V1, to resolve the ambiguity. This is as if to look up information from a blackboard. However, I hypothesize that this happens only in central vision due to limited brain resources. So there's a functional difference between central and peripheral vision. Therefore, central V1 is for recognition, which is helped by the recurrent feedback query. The bottleneck motivates both the V1 saliency hypothesis and the central-peripheral dichotomy theory.
Okay, so this is more or less in the face of what we see yesterday, such a ridiculous situation. Yeah, they say, well, what can we do? We have to redefine vision. Okay, the vision really is you have a bottleneck, you have a select, and then you have to see in spite of the bottleneck. And then it's a kind of a redefinition of a problem. Maybe it's a wrong definition, maybe it's a right definition. But because the previous research have been just having difficulties, maybe in one way, let's see whether we have a new definition of a problem can make some progress. That's the idea, yeah? And of course, when you say definition, actually you have a theoretical proposal. You have a framework. And all because inspired by the bottleneck, you have to select before, you have to see after. That's the idea, okay? So let's continue.
Hypothesis and the central-peripheral dichotomy theory. Motivated by these considerations, a central-peripheral dichotomy is proposed. Firstly, Peripheral vision is mainly for looking or selecting, and central vision mainly for seeing or decoding. For example, this location is in the peripheral visual field before the gaze shift. So the peripheral vision plays a big role in deciding which peripheral location should be selected into the attentional spotlight. Then the central vision focuses on decoding the selected inputs.
Same time they went in there.
Okay, so this is an example yesterday we experienced.
With-
Okay, stop the talking. And so the idea is, yesterday we went through this experience that we didn't see it, we just select. Okay, the gaze shift is to select. Okay, and then the selection is by your peripheral. You can say, oh, go to the peripheral left, or go to the left or right, or top down. Your peripheral vision is kind of deciding for you, go this way or that way. Okay, you better go to the way that's important, where the food, people you love, that predator, or run away from the predator, and so on. And then once you go there, you say, this is the food I want. And this is the idea. Yeah, you can see how people, and some of you said, I did not go there, and my gaze did not go there. The idea is, you actually, as I said, almost 100% of you actually looked that way. But you did not realize you did, okay? Just like when I asked you, how many times you move your eyes, theoretically you know it's 180 times per minute, but you feel only 5 times, yeah? Because most of these are before you recognize, so you did not realize you did. Okay, so that's looking and seeing. You can say vision is roughly equal to looking and seeing. And encoding is just before it. Okay, so that's the idea. So let's continue.
Dichotomy can be tested through some of its predictions. For example, peripheral vision is more easily fooled to have certain illusions by misleading feed-forward inputs. And central vision is more biased for prior beliefs or expectations that require feedback to implement. And central vision should have stronger effects of backward masking, which manifests top-down feedback for decoding. Before we dive deeper, let's have some fun. Here you should see some flashing black dots, but not...
Yeah, do you see? They are illusions, huh? And they are only where you're not staring at. If you stare at the dot, it's not flashing. So if it's in your central vision, it's not flashing. Only in your peripheral vision, yeah? So isn't that something? The idea is your peripheral vision is not its job. Its job is to direct your gaze. Okay, so it's like a job share in vision. Central vision is to recognize, peripheral vision is to say, look this way, that way, yeah? Okay, yeah. That actually I do not understand. So there's lots of things I do not understand. So that means there's a lot of these research projects lurking there for people to come do it, yeah. So this only notice that it's in peripheral vision. Okay, so let's do another one.
Here you see illusory rotations.
Another one.
Visual crowding.
Sorry. Stop. Oh. So let me stop this so you can see it. This is a Japanese guy who's so good at just designing these things. This is a static image. But do you see it's not static in your view, yeah? And only outside where you're staring at, yeah? So again, there is partial understanding how this works.
Sorry, you can define what is an illusion, because in my opinion, it's not clear why central vision is more biased while peripheral vision is more easily fooled by illusion.
Yeah. This is because the idea, remember, central vision, when it cannot see clearly, it will go back and ask for more information. So the bottleneck. Peripheral vision, the hypothesis is they don't go back. The reason is, maybe I just speak like this. If your brain has n neurons, if all neurons are connected with each other, your brain will be too big. Yeah. So a lot of space in the brain is occupied by neural fibers. And so every time you have these neural fibers, you are occupying space. So if you don't want your brain to be too big, you only do it for whose job it is. Central vision's job is for recognizing, so only do it for central vision. Yeah, that's the idea. And so therefore, peripheral vision only has feed-forward impoverished information through the bottleneck. And this impoverishment can lead to illusions. And I am going to predict some illusions from the theory and test it on you. You can see it. Do you see it or not? Yeah? In vision science, predicting illusion never happened before. But if you have a good theory, you say, well, can it predict illusions? No. So therefore, if we have a theoretical framework that can predict illusions, that will be indicative that, well, if you really understand that's the case, let's predict something. Yeah. And I derive for you how these are predicted in today's lecture. Okay? Good. So, thank you. So here's another one. This is just for fun, and then let's go on.
Okay. The snakes, and also only beyond your central gaze. Visual crowding demonstrates that visual ambiguity is difficult to resolve in peripheral vision. Let's look at the flip tilt illusion predicted by the central peripheral dichotomy. The central peripheral dichotomy first states that the peripheral vision is mainly for looking and the central vision is mainly for seeing. Furthermore, since an information bottleneck starting from V1 means that information feeding forward from V1 is impoverished, so therefore in central vision, when the impoverished information is insufficient for recognition or decoding properly, a top-down feedback is used to query for additional information to help disambiguate between possible perceptual outcomes. In peripheral vision, this feedback query is weaker or absent. This predicts that the peripheral vision is more prone to visual illusions from misleading inputs. And let's look at one such predicted illusion.
Okay, so let me stop again. Yesterday, remember we were doing maximum molecular decoding. We were saying, oh, is the outcome A or B? Sometimes you are very certain about A, sometimes you're very certain about B, sometimes you are not certain. This is a non-certain situation. Your decoding can be erroneous. And this error is illusion. And then you say, you don't give me enough information. Can I have another neurons firing? Then you can be more certain. This is when central vision go back and ask for more information. Okay? So let's see how we will have illusions and how we will not have illusions. Okay, the flip tilt illusion is one such example.
In this image, you see many vertical segments. Each is made from a pair of dots of the same color, black or white, and let's call them homopairs of dots. There's no illusion here. Here is another image of vertical segments. Each segment is a dot pair made of one black dot and one white dot. Let's call them heteropairs of dots. We predict that if you fixate your gaze to the center of the left image so that the right image is in your peripheral vision, then you should have an illusion of the segments in the right image that they are tilted horizontally.
Do you feel that way? Difficult, huh? Trying to fixate your gaze here. Okay, just stop. Let me, anyway. fixate your gaze here.
That the
Stop. Or maybe I can just pause here. There's a pause button. So go
the
like that. Pause. Okay. So fixate your gaze here and trying to look this on the corner of your eye. Do you feel it's horizontal? Difficult, yeah? And so in psychophysics experiment, people say, I don't know. Then you say, you have to say horizontal or vertical. And when they have to say, almost 100% time, they say horizontal. But because you don't know, you cannot. So let's try something more obvious, yeah? So.
each is made from a pair of dots of the same color, black or white, and let's call them homopairs of dots. There's no illusion here. Here is another image of vertical segments. Each segment is a dot pair made of one.
Anyway, we have seen this, so let's just go to the next one.
This image made entirely of homopairs of dots. Fixate your gaze to the central cross, you should see a large ring because there are many homopairs parallel to the tangent of the ring. Other homopairs in the background are randomly tilted. There's no illusion here. Now look at this image and fixate on the central cross. There is a ring at the same location as before, but somehow you cannot.
Can you see it? Can you see the ring? Difficult, right? So this you cannot see the ring, this you can see the ring. Okay, it's interesting. So let's.
Identical to each other, except that every second dot pair on the ring is replaced by a heteropair of dots. As your gaze is on the central cross, the ring is in your peripheral visual field. The flip tilt illusion makes these heteropairs appear orthogonal to the ring. This breaks the continuity along the ring so that you cannot see this ring when fixating at the central cross. If these heteropairs are made orthogonal to the ring, then the flip tilt illusion should make them appear parallel to the ring, to make the ring more visible as a result. Let's try to do exactly this in image C. Image B and C are identical to each other than these heteropairs of dots along the ring. In C, they are orthogonal to the ring, and in B, they are parallel to the ring. If you fixate to the central cross in B,
Yeah, which one is easier for you to see the ring? C or B? C, right? And so all of you can see this illusion. You are cheated by your own brain, yeah? And so only when you don't look at it, okay? If you look at it straight, it's in your central vision. Don't look at, just casually look and say, I can see the ring here, not a ring there. I even did it on the Twitter. In the poll, people say, yeah. Anyway, it's interesting. You can do psychophysics on social media just for fun. And so, however, now move your gaze to this. Now it's in your central visual field. Then you don't feel it's a very good ring. But you move your gaze there, oh, that's a very good ring here. No. Because now it's in your central visual field. Yeah. Exactly the same, other than these heteropairs of dots. Everything, you see, this is same as that. Everything is same. Even the noise in the background, everything the same. Yeah. And so therefore, you can predict that and then say, how did you get that prediction? Let's see. Okay. So continue.
the ring should be more visible in C than in B. However, if you move your gaze to the ring segments, then the ring is more obvious in B than in C, because now the ring segments are in your central visual field. Let's understand this illusion. This depicts a receptive field of a V1 neuron tuned to horizontal orientation. This receptive field has an on subfield and an off subfield. If a vertical heteropair is placed in such a way so that the black dot is in the off subfield and the white dot is in the on subfield, this neuron should be activated, even though it is tuned to horizontal orientation. This same neuron can also be activated by other visual input patterns, such as a horizontal homopair, another horizontal homopair, or a horizontally oriented Gabor shape. However, a vertically oriented residue field for another V1 cell cannot be activated by this vertical halo pair of dots. So this vertical halo pair of dots activates V1 neurons tuned to orientation orthogonal to itself. Given a vertical halo pair activating a V1 neuron tuned to horizontal, imagine that the information bottleneck is so extreme that this V1 neuron is the only neuron to send this information forward to higher visual areas. Higher visual areas know that this neuron is tuned to horizontal orientation. However, when they receive the activation of this neuron, they have to guess which of these possible retinal inputs might be responsible. So the perception should be ambiguous. Without further information,
Okay, so apply the maximum likelihood decoding from yesterday. A or B. A is horizontal, B is vertical. What would you say? Yeah, based on this one neuron response, the maximum likelihood is horizontal. Okay? And it's an error. The error is illusion. Does that make sense? Okay, so that's what happened. So let's continue. Resume.
should state that the retinal input is horizontal. And this is the flip tilt illusion caused by an information bottleneck from V1 downstream. If higher visual areas could compare each possible retinal input with the actual input in V1 to verify which perceptual hypothesis is actually correct, the perception will be unambiguous. This feedback query for more information is achieved by generating a would-be input for each perceptual hypothesis and compare it with the actual input in V1. This whole process is called feed-forward, feedback, verify, and reweight, or FFVW, which is a paraphrase of analysis by synthesis. This feedback is available in central vision according to the central-peripheral dichotomy. Therefore, central vision does not have the flip-tilt illusion.
Okay, maybe it's a time to pause. Any questions? Okay, no question. Good. So you may want to say, what is this trying to do? Let's say this, yeah, okay.
Using the picture, but I don't understand what is the meaning of actual meaning of illusion.
What's the meaning of what? A bit louder.
Illusion, like in the picture you explain, like when we have a black and white, there is no illusion. But when we have a pair, like heteropair, so we have illusion. But I don't understand, like why.
Okay. Remember yesterday we have maximum likelihood decoding, and the maximum likelihood decoding is not always correct, remember? And so when you say something incorrectly, that means you actually see it, yeah? Seeing something incorrectly is, by definition, an illusion. Say it again. Illusions at it.
Error?
Illusion is an error, yeah. Oh, it's a dog over there, but you see it as a cat. It's an illusion, no? There's nobody there, you see somebody. It's an illusion. Yeah, when things are flashing, when things are moving, it's an illusion. It's not flashing, it's not moving, yeah? So your perception made an error. So in this case, we just applied our maximum likelihood decoding, found the response only one V1 neuron, then you will make an error, okay? And yesterday we also say that you don't have to base one V1 neuron to make a response. You can have two V1 neurons, three V1 neurons, and then maybe you will not make an error, yeah? So when this comes back to get more information, is to get another V1 neuron response, yeah? So you say, oh, let's say V1 has 100 million neurons, and this one V1 neuron out of 100 million neurons, that's a theoretical asymptote. theoretically, you could treat it to extreme asymptote as we just base our decision based on V1 neuron. Not too bad. Yesterday we talked about how one empty neuron is equivalent to the whole monkey. So one V1 neuron is not too extreme, yeah? But nevertheless, let's say that. And then you say, let's say this is V1 neuron number 10 out of 100 million. Can I go ask V1 neuron number 11, what is your firing, yeah? So that's the idea. So you go back, you can ask, what about V1 neuron number 11? You know, it has a recidiv field here, and it's not activated. Then you get 2 V1 neuron, you can get better decoding. And you can say, maybe also V1 neuron number 12. So you ask V1 neurons that's relevant to distinguish between these 4 situations. You don't ask V1 neuron number 550, maybe it's recidiv field somewhere else, irrelevant, okay? So you come feedback to ask for the relevant information. You cannot ask for too much information because everything has to go through the bottleneck, yeah? It's a little bit, I say, ask me only 2 questions, not more. Then you have to say which 2 questions. After 2 questions, you can't do it anymore, yeah? And so this feedback signifies visual understanding because I understand what's the situation, what is the ambiguity, which neuron I need to go ask for more information. Okay? So that's what happened. Any other question? Okay. No? Okay.
So basically in the example that you gave us that had like rotating, because I saw the image rotating, and sometimes I saw it as a fixed image. So is it like what you just explained it now? So like you are asking for more information and it's accurate, and then you are doing it again and again? Is it that?
So one way to ask for more information is move your gaze to the rotating bit. That's you select. You're asking more information. It's like selecting information. You move your gaze to it. Oh, it's not rotating. You just corrected your error. You errorly think it's rotating there. Then you look. Now it's in your central visual field. You can ask for more information more easily. It's not rotating. Yeah. Then you corrected your perceptual error. Yeah, but just like in the world, some bits are moving, some bits are not moving. You don't assume everything is moving or everything is not moving. Yeah? Yeah. You go to the forest, could take a walk. You cannot say, either everything is moving or everything's not moving. Some bits can be moving, some bits not. And your decoding tells you, some bits are moving, some bits are not. It just coincidentally, the bits you decode is not moving is in your central visual field. Good. Okay.
How we have, is it like experimental observation that there is a bottleneck? There is a bottleneck to attentional bottleneck, or is it like an hypothesis that we're going to test later?
Remember, we talked on Friday. It's experimental observation. We have a bottleneck. Okay. Remember, we measured how subject can tell which image is shown, and they could not tell. Remember, we also show you 2 images. Can you see the difference? You cannot tell. So all these are experimental data. I just use these data on yourself. Were you showing that you cannot tell the 2 images that's different? Yeah. So you have one single data point by your own observation. And the reason I'm showing you all these demo, they are not demos. You can treat them as a psychology experiment, and you are taking data with yourself. Yeah? And so you say, indeed, I have a bottleneck. Looks like I cannot tell the difference. And then I also show you where 1950s experiment. Remember that one? Yeah. So therefore, these are not assumptions. Okay, they are actual data. And based on data, we're trying to understand how vision works. Okay. So it is very it is not a very traditional way of doing physics, you can say. We are doing physics, but in the brain. And a lot of these definitions, what do you mean by illusion? What do you mean But bottleneck, is that really data assumption? You know, actually we are doing exactly the same way as in physics. Here is observation, but then because we normally think about this, and so therefore getting comfortable, you realize it's actually very traditional physics, yeah? Okay, but this is why today we need more question and answer, because this is an unusual way of doing things, yeah. Okay.
So I don't understand, like, I thought like illusion maybe is when I'm not giving my attention to that particular area. Maybe if I'm giving my attention to a fixed area, the other area will seems not to be clear. For me, maybe that's illusion. And I don't understand also this majority vote. Like you have only 2 points. Like.
Okay, let's have another more obvious illusion. Maybe then ask again. Yeah, is it okay? Okay, so let's resume.
Let's choose another peripheral illusion, reversed 5 motion. A pair of dots separated in time gives motion. This pair gives motion to the right, and this pair gives motion to the left. However, if the contrast polarity flips from one dot to the next dot in a pair, the perceived motion direction of motion is the opposite of the actual motion. This is the well-known reversed 5 motion illusion. Here is a demonstration of the reversed 5 motion illusion. This appears to constantly move forward in a clockwise direction. But let's look closely at this element, for example. It simply moves back and forth, back and forth. In its forward motion, the contrast polarity does not change, say from a black-colored oval to another black-colored oval. In the next time step, it moves in a backward direction and reverses contrast from black to white. In the next time step, it moves forward again, white to white, without changing the contrast. And in the next time step, it moves backward again, from white to black, changing the polarity. And the cycle repeats to give a constant forward motion illusion. This reversed phi illusion.
Did you see that illusion? Is it more obvious it's an illusion? Is it?
Reversed phi motion illusion. This appears to constantly move.
So this is an analogy to the orientation illusion, flip tilt illusion, but this is a space-time illusion. The previous one is a space illusion only, orientation in space. Motion direction is a space-time, exactly the same thing. So let's try to derive this, yeah? Understand it. Okay. So let's try to understand this.
This reversed phi illusion can be understood by making an analogy with the flip tilt illusion. We recall that this flip tilt illusion is because a hetero pair of dots can activate a V1 neuron tuned to an orientation orthogonal to its actual orientation, and does not activate another V1 neuron tuned to its actual orientation. Consequently, when V1 sends this activation forward, higher visual areas can be misled to believe that the responsible retinal input is oriented at the preferred orientation of this neuron. This misleading situation occurs because an information bottleneck prevents V1 from feeding forward other useful information, such as activations from many other V1 neurons tuned to other locations, orientations, and spatial scales. An orientation in space can be extended to an orientation in space-time. This visual input at spatial location x1 and time t1, moving to a spatial location x2 at time t2, can activate a V1 neuron with this spatial temporal recessive field oriented in this way in space-time orientation. This neuron is therefore tuned to this rightward motion direction. An opposite motion direction could not activate this V1 neuron. However, if the dot changes its contrast polarity from one time step to the next, this neuron can be activated to give the reversed phi motion illusion. Analogous to the flip tilt illusion, this illusion is weaker in central vision because top-down feedback to query for more information is available in central vision according to the central-peripheral dichotomy. Therefore, we are not fooled by this illusion when our gaze is fixated here to put this element in our central visual field. But we can sense this illusion quite strongly when we move our gaze quite a short distance away.
So now is it clear? Yeah. So with this analogy, and you can say, amazing. Indeed, if you stare at it, you can see it's moving back and forth. Okay? So we can push this analogy further if that's correct. So the next analogy is reverse depths. That's why we make you wear this later, okay? So let's first see the theoretical television, how it works and so on.
Vision, reverse depth. Just as a pair of spatial dots gives a spatial orientation or another orientation, a pair of corresponding dots in space-time gives one motion direction, and here is the opposite motion direction. A pair of corresponding dots across two eyes gives a 3D depth. In this example, the two dots have the same retinal location in the two eyes, so the binocular disparity is 0, meaning that this dot is roughly in the same depth plane where the gaze is fixating in the 3D space. If the dot moves closer, the retinal locations change to give a positive binocular disparity, and therefore a positive disparity signals a closer depth. Conversely, if the dot moves further away, the binocular disparity is negative. V1 neurons are tuned to binocular disparities. This dot in the first example should activate V1 neurons tuned to 0 disparity. This should activate V1 neurons tuned to a near depth, and this should activate V1 neurons tuned to a far depth. One can therefore make a random dot stereogram to depict a 3D scene with a central disk of random dots in front of a surrounding ring of random dots. Start with an image of random dots for the left eye. The dashed circle is not part of the image, but it encloses the dots intended for the central disk. Then make a copy of this image for the right eye. This is an example black dot matched between the two eyes. Another example white dot matched between the two eyes. This shift of the central disk gives a positive disparity to this disk, moving the disk in front of the surrounding ring in 3D depth. Just as one can make a reverse motion direction by corresponding a black dot with a white one, one can make a contrast reversed or anti-correlated random dot stereogram to create a reverse depth. Now each black dot in one eye corresponds to a white dot in the other eye. The surrounding ring still has the normal match between the dots. The top and bottom stereograms have the same disparity value for the central disk. However, V1 neurons respond to this bottom stereogram as if the disk is now behind the surrounding ring. Just like the reverse phi motion activates V1 neurons, preferring the opposite motion direction. When human observers look at this stereogram by central vision, they see the disk as neither in front nor behind the surrounding ring. Although V1 neurons send the reverse depth signals forward.
Okay, so far so good. Any question? Okay, so now let's theoretical argue, derive further, okay?
Can verify whether the V1 report is correct and realizes that this report is misleading. Therefore, this report is vetoed and no reverse depth is perceived. So, top-down feedback in central vision enables vision not to.
Okay, so this is again, people may feel, what do you mean by illusion? What do you mean by vetoing? This is again like yesterday doing decision making between A and B. Perception, do you see A or B? And here you have initial evidence saying A, and then this initial evidence for A is deleted, but no evidence for B, so therefore neither A nor B. Okay? So that's what happened. In central vision, the decoding is, I don't know. I don't know is a valid decoding. You can decode that way too, yeah? You say, I'm not sure. Okay? Because originally I thought it was A, but I think it's just cheating, okay? It's cheating, lying, fake news, whatever you call it, right? They corrected this fake news, then you don't have the news. So now it's no news, neither in front nor back, yeah? Imagine it has the opposite news available, then you will see the opposite news. But there's no opposite news. So let's continue.
Well, if peripheral vision does not have such verifying feedback, according to the central peripheral dichotomy, then the feed-forward V1 reports will not be vetoed, and they should lead to the reverse depth illusion in a peripheral visual field. This prediction has been experimentally confirmed. To demonstrate this illusion, let's start with normal depths without this illusion using this random dot stereogram. Left eye image and right eye image. Over the binocular corresponding dot pairs are homopairs, and this stereogram depicts a central disk in front of a surrounding ring. Try to free fuse these two images, and you should see the disk at a different depth from the ring.
Can anybody free fuse? Maybe mostly not. So later we will use these glasses. Let's continue with this.
The central disk has the same binocular disparity as that in the top stereogram relative to the zero disparity ring. However, all the dot pairs for the disk are non-hetero pairs. A black dot in one eye corresponds to a white dot in the other eye for the disk. If you free fuse this bottom stereogram, you cannot see whether the disk is in front or behind the ring. This is because you usually do this free fusion in your central visual field.
Okay, so let's try it. Put on your glasses, and in the top, you should see something very similar to yesterday. Okay, in the bottom, what do you see? In front or behind? Stared at in your central vision, you cannot see. This is how confusing. Your perception just decided, I don't know. Yeah? Do you have a pair of glasses? You don't need? Oh, there's more if you like. You can take more. And so therefore, in the bottom, you say, I cannot see. Now let's use a trick. Don't look at in your central vision. Can you do at the bottom? Don't look at the central vision. Trying to look, let's say, look here or look there. Trying to look at my mouse. Okay, look at my mouse and then trying to see the bottom. Oh, it's a forced choice guess. Okay, I'm not telling you whether the bottom is in front or behind. You tell me, how many people, so we are doing statistics here. So when people come to my lab to do experiment, they say, I don't know. I say, you have to forced choice report, front or back. Then they do it like 100 times, then you say, 70 times they say one thing, 30 times they say another thing. That's twice as many, one thing, another thing. So that's, you can see they do it. And I'm not going to make you do 100 times. I'll just make you say how many people see this way, how many people see that way, okay? So look at the bottom, and try to look at the bottom, not with your central vision, trying to look like, put your gaze here or there or something like that. How many people see the disk is in front? Raise your hand, okay? How many people see the disk is behind? Raise your hand. Look, most of you see the illusion. It is behind, okay? So this is how you are uncertain, but if you're forced to do it, some of you did not raise hand at all. So That makes me not having data. You raise your hand, I have more data, then you have a stronger statistics, okay? When people come to my lab, they volunteer, each time they have to push the button. Okay, that's what happened. So, very good. We have almost 3 times as many people seeing the behind. It turns out that this disparity is same as that disparity, but you see the other way, yeah? Okay, very good.
That the top-down bias in ambiguous perception as another manifestation of the central-peripheral dichotomy. We recall that one of the predictions...
Sorry, I was actually doing something else, but somehow it did not show. Where did it go? I forgot to show. So it's in another, maybe I forgot to save it. So the idea is then people say, are you sure this is a whole thing? Central vision is, the idea is central vision send feedback to overcome the illusion, yeah? Yeah, let's go back. So the idea is the central vision send the feedback. I say, well, there could be another theory. Central vision have higher resolution. That's why it's not fooled by misleading input. So therefore, you can say this theory maybe is not right. Maybe not because central vision go back and ask for more information, but because central vision has higher acuity, resolution, spatial resolution. And so therefore, as most recent, this is not even in the video in the online course, we try to predict something else to say central vision does. That's another prediction. Okay. So the idea is central vision does not see it, maybe because it has higher resolution. You have another peripheral vision have poor resolution. That's why you get misled. So another prediction is, what if we cut this feedback? Let's say we cut this feedback. If you cut this feedback, even though central vision still has more samples of photoreceptors, if the theory is correct, then central vision should see the same illusion. That's fair, isn't it? They say people come to my lab and do experiment, and I open their brain and cut their feedback. I'm not allowed because I don't have ethical approval for doing this. So how can I cut their feedback? So then we have a trick. The trick is the feed-forward information tells you the fake news. And then you go feedback and say, oh, I want to look at another neuron. What other neuron can you look? Look for the neuron that they did not send you the information. Which neuron did not send you information? Monocular neurons, remember? Monocular neurons never go beyond V1. So if you say, well, there is a neuron that is a binocular, look at this location and say, it's a disk behind. This binocular neuron got fooled by my hetero pair of dots. But if I look at a monocular neuron at this location, it says it's a black dot. And this monocular neuron is tuned to left eye input. And I look at another monocular neuron at the same nearby location, but it's tuned to right eye input. It says it's white dot. Okay? Then you put 3 neurons together. One monocular neuron says left eye is black dot. One monocular neuron says right eye is white dot. One binocular neuron says this is a dot behind. These 3 neurons are not talking consistently. Then you can veto it, okay? And so imagine when I go back to look, I suddenly take the original input away. You cannot look anymore. Is that fair? I can do that, yeah? I just show you the image very quickly. I show you this thing so quickly. By the time you go back to look, I removed it. This is a particular experimental trick called masking. This is called backward masking. You just pull the rug under somebody's feet. That's what happened, okay? And so we do backward masking. You just remove the input. And unfortunately, when you do that, people say, you do it so quickly, I cannot see. If I cannot see, I do not see its back or front. Yeah. So what can you do? What we can do is, rather than completely remove it, I generate another pair of random dots stereogram. But the random dots are reinitiated, put in some other random location. That's all. So therefore, each time they go back to check, it's another image they cannot check. Each time, so I just keep on doing this. Every 10 milliseconds, I just generate another pair of image for the same disk, for the same ring, for the same fake news, but I just randomly generate different set of random dots. That's all. Okay? And so I do that, and then they see all the same feed-forward fake news, but they cannot feed back to check. That's what happened. And do you like to see that? Put on your glasses. This is when you look at the bottom one, you cannot tell whether in the top you should see this disk is in front, this disk is behind. Do you see that? If you put the blue one on your right eye, you should see this is in front. Or maybe because this is open. Can we pull this close so you can see? Now is the situation that I let you look without. Now is the situation I let you look at this without pulling the rug under your feet. Okay? And then, if you don't look away, it's hard to tell. Put this in your central visual field, whether this is in front or behind. Okay? So in the top, imagine. Even if I flicker it, you can still see it's in front and behind, right? Correct? You see this disk is in front, this disk is behind. Let me do it again. Okay, so, okay, you see it's not flickering. It's just this is in front, this is behind. But if I flick, it's still the same, yeah? No problem. Now in the bottom, you cannot tell whether this is in front or this is behind, in front. I can tell you, okay, they are opposite. Which opposite way? Okay, now stare in your central vision, and I'm going to flick it. Now can you tell, stared in your central vision, which one is in front, which one is behind? Okay? You can more easily tell. Okay, for those of you, just say which one is in front, okay? The left one is in front, raise hand. The right one is in front, raise hand. And this time it's almost the same. So this experiment is a bit. But when I'm in my lab, you say this one most people see behind, this one people see in front. If you give me more data, okay. Some of you did not raise your hand.
Because I think some of us like here is not clear. Like when I put my glasses and look here, I don't see the middle. There is nothing in the middle. Make the light.
Oh, can you maybe turn off the light? Yeah, is there a way to turn? Is there a way to turn off the light? Yeah. It's not an ideal situation, so you're all guessing.
Like when I put my glasses, actually I almost feel that there is nothing in the middle.
You almost see there's nothing in the middle. Interesting, yeah. So. And of course, this is my laptop. My laptop has 60 hertz refresh rate. So it's not like the next image comes in 10 milliseconds. It's rather than 18 milliseconds later. So if it's 10 milliseconds later, it's even easier. So that's the experiment we did to show that the theory is, yeah, then how much time do we have? Okay, We still have about, okay. Okay, so this is,
So these higher brain areas are related to questions. Because always it's like, did I see an illusion? And we move to check if it is an illusion. Do I see something? So these higher brain areas are connected to areas of logical questions.
yes, so this theory does not quite say which are the higher areas. It just uses a bottleneck and the knowledge of V1 neurons to predict illusion, that's all. And by predicting illusion experimentally verified this way, the idea is then we can motivate neuroscientists to look which higher area does that, yeah? So a little bit like, oh, now we only know the solar system, we know nothing. And then when people look, oh, there's a Milky Way and things like that. And so far you can say this theory is, you can see the other illusions are predicted using very simple knowledge. The simple knowledge we have assumed are just these V1. And this knowledge is classical from 1960s. Okay? The only thing we add on top of it is a bottleneck, nothing else. Yeah? So all you need is V1 neuron properties, which is classical. In our encoding lectures, we already know this knowledge is experimentally established. The only new thing is the bottleneck. And what we learned about how do you do maximum likelihood decoding. But maximum likelihood decoding is just mathematics, nothing else, yeah? And so these things put together enable us to predict illusion, but does not enable us to say, what is this higher visual areas? Is it V2, V3, V4? We do not know. But hopefully this gives enough of a motivation for the neuroscientists to say they go discover, yeah, which area. And exactly how does this feedback work? And how does it go back and look? Well, we know neuroanatomy fibers, the feedback fibers existed, but they look so messy, not understandable. But then once you have this prediction, then become more concrete. So for example, you can make monkey do this experiment, no? You can make monkey do in front or behind. And then you measure the monkey's neurons at the same time. Yeah? Monkey can be trained to do that. A good question. Any other questions? If not, let's go to something more exciting, okay? Top-down bias, and yeah, let's have a look at this.
In ambiguous perception as another manifestation of the central-peripheral dichotomy. We recall that one of the predictions of the central-peripheral dichotomy is that central vision should be more biased for prior beliefs or expectations that require feedback to implement. Let's look at an illustrative example. Let's say that we present these images to the left and right eyes respectively. They are constructed such that when they are added together, the result is a grating that is slightly tilted clockwise from horizontal. When they are subtracted from each other, the result is a similar grating but tilted anti-clockwise from horizontal. We are interested in binocular summation and difference channels because V1 represents stereo inputs this way in its neural population activities. Anyway, such inputs give ambiguous perception as to whether the grating is tilted one way or another. We can ask observers to report by forced choice whether the grating they see is clockwise or anti-clockwise tilted from horizontal. So they will have a perceptual rivalry not between the inputs to the two eyes, but between the summation and difference signals. Across different trials, the tilt in the summation channel can be clockwise or anti-clockwise, randomly and equally likely. The visual inputs are made in such a way that the gratings in the summation and the difference channels have the same contrast. So if these contrasts determine the outcome of the rivalry, then we expect that in about half of the trials, the reported tilt direction is from the summation signal. This is the result, with the vertical axis marking the fraction of trials in which the observers reported the tilt in a summation channel. We see that in about 2/3 of the trials, the observers reported tilt in a summation channel. Why does perception prefer the summation signal? Both channels could send their signals forward with equal strength, but opposite messages about the direction of tilt. However, due to the attentional bottleneck, higher brain areas do not know whether a message arises from the summation or difference channel, because they do not know whether visual inputs come from the left eye or right eye. They just know that message 1 and message 2 are received, and these two messages disagree on the direction of tilt. When the higher centers examine the first message to see whether it makes sense, it could reason with its internal model of the visual world that if this message is correct, then it must be shown to both the left eye and right eyes. Would be best to go back to the retina to verify this, but the best it could do is to go back to V1 to check. And it would then check with the signal in the summation channel, which is a proxy for the inputs to both eyes. This is because prior knowledge says that the summation signals should resemble both the left eye's input and the right eye's input, since in typical situations the two eyes receive very similar inputs. This assumption is correct in typical cases, but not in this particular example. But the higher centers do not know this. Therefore, the brain's prior makes this feedback verify a message about visual inputs by checking whether this message agrees with V1 signal in the summation channel. In our example, this verification should find confirmation to this message 1. When the higher centers consider the other message, the same reasoning makes them verify also with the signal in V1 summation channel, and this verification should find disagreement. Consequently, the weights of the two messages are modified to favor the one confirmed by the verification, and that's why the summation signal is favored. This whole process, including the feed-forward, then feedback to verify the feed-forward hypothesis of visual inputs, and then, according to the outcome of the verifications, modify the weights for the original hypothesis about visual inputs for the final perceptual outcome, is summarized as feed-forward, feedback, verify, and reweight, in abbreviation FFVW. Interestingly, when the same behavior task is done in peripheral vision, data illustrate no bias for the summation channel. You may ask whether this is because observers cannot see clearly in peripheral vision, so they just report it for the task randomly. The answer is no, because they can do the task in peripheral vision very well if visual inputs are not ambiguous, when the same grating, slightly tilted, is shown identically to both eyes. Weaker or no bias for the summation signals reflects a weaker top-down feedback for verification in peripheral vision. Therefore, central vision is more biased for prior beliefs or expectations that require feedback to implement, such as in this task. We can verify our hypothesis further by extending this experiment. Observers can view the visual input longer to give more time for feedback to take effect, or shorter so that feedback has less time to act. Indeed, the bias in central vision increases with time available for the feedback, but not for peripheral vision. We can extend this task to perception about motion direction or color, and the biases for the summation channel are again found to be stronger in the central visual field.
Okay, any questions? Yeah, okay.
When we change the pictures, like the right eye, we show the one to the left. When we switch the picture, it gives the same result.
Same result. Correct, yeah. Good, okay, yeah. Why is what on the summation? Or feedback. The reason is, remember, earlier when the central vision has to feedback and find the information, I say, oh, neuron number 10 tell me this, I need some information from neuron number 11. So the central vision needs to feedback for the relevant information. And the most relevant information is the summation channel because it wants to know what's the left and right eye input, but it cannot go all the way to the retina. That's why, yeah? So the feedback, remember, signals visual understanding. It signals that I need to know what information I need. And I think the relevant information is in the summation channel because it actually wants the left and right eye input. Yeah, okay, good. Any other question? Yeah.
Can you explain again what do you mean by bias? Why there's
Bias. So the idea is you need to, remember we say that the two eyes are correlated in our efficient coding. The two eyes are correlated. And this is a statistical knowledge in our memory, we know that. Because the two eyes are correlated, you want to know what's the left and right eye input, you should go to the summation. So it's a bias to check for the summation channel, not check to the difference channel, because I have a prior knowledge to know that my two eye inputs are correlated. Yeah? Okay? This bias, you have a lot of these knowledge, and because of this knowledge, you will be able to see the duck. You will be able to see the triangles and so on, yeah? Because these are all your bias. If you've never seen a duck before in your life, you could not see the duck here. Yeah? Okay? So we recognize things despite very little information coming because we have a lot of knowledge. If I see your face, actually it's very blur, but I have a knowledge face should look like this, then I see clearly, despite very poor signals, yeah? This is a very poor signal of a duck, but you can see the duck very clearly because you have a bias, knowing what the duck is, okay? Here you see a triangle, why? Well, in your life you've seen lots of triangle before. So you can imagine things, okay? So that's very interesting to look at our imagination. And this imagination make you prejudiced, biased. You know, all these biases are human behavior. We have these, remember yesterday when we talked about Bayesian decoding, when we do maximum likelihood decoding, is when there's no bias. But if you have Bayesian decoding, you can look up Bayesian decoding in some of the videos, then you will have your bias, okay? Because you have this knowledge of the prior. Okay, good. Any other question? That's right, because the peripheral vision does not know which one is summation channel, which one is difference channel. It receives two messages. Yeah, so let's go to the yesterday. Yesterday, remember yesterday when we say, when we had a situation of decoding, you say, let's say decoding just found one neuron. Okay, let's not having any speech, so I can control myself. We have one neuron. This neuron can fire around here, then you are very certain. Fire around here, you are not certain. But if it's fire near the boundary, you are not certain. Yeah. And so you may have two neurons. One neuron says it's one way, another neuron says another way. Putting two neurons together, you are not certain. Okay, this is one neuron decoding. You can also have population of many neurons. Yeah. Population 1, 2, 3, 4. One neuron says this, one neuron says that. What can you do? Okay. And so therefore, you can imagine in our situation, we have, let's say, both neurons from this channel, from that channel goes forward. However, the neurons' identity are removed. Okay, so let me go there. All right, they feed forward, both neurons. And then the peripheral vision received this neuron signal, that neuron signal, but did not receive the signal that this neuron is come from. Ocular summation, there's just two signals. And with these two signals, it doesn't know what to say, so it will have 50-50. And that's why it's 50-50. It doesn't know. Yeah. Good. Any other question? Okay, no more. So let's see. Okay. Oh, it was here. Yeah. Sorry. So, yeah, this I already done. Okay. Now let's really do this imagination, because our vision is imagination. Our imagination is our thinking that can go very far. That's why I say when you study vision, you may end up studying thinking. Lots of things, yeah? So look like imagination further. Okay? So let me put on this. Imagination further.
In depth perception, using random dot
Top-down
stereograms.
feedback is imagination, a lot of it.
Let's remind ourselves that we can make a random dot stereogram depicting a disk in front of a ring. This is by having a disparity between binocularly matched dots for the disk, so that this disparity signals a near depth surface in front of the ring. We can also have a contrast reversed or anti-correlated random dot stereogram for the central disk. Here, a black dot in one eye corresponds to a white dot in the other eye. Here, the spatial disparity value is the same as that in the stereogram above. But V1 neurons respond to these contrast reversed heteropairs of dots, as if the depth is reversed. In this example, as if the disk is behind the ring. However, this reversed depth is not perceived in central vision, since according to our hypothesis, the misleading V1 signals are vetoed by top-down feedback. This reverse depth is perceived in peripheral vision where the top-down feedback is insufficient. Let's focus on central vision to examine the feed-forward and feedback processes. We make a hybrid stereogram such that some dots are contrast matched between the two eyes. They are homopairs of dots, and others are contrast reversed heteropairs of dots. They have the same disparity value, but homo and heteropairs generate opposite depth signals in V1 neurons. We can ask, what will be the perceived depth for the central disk? We can compare the perception with this noisy stereogram, which is the same as the stereogram above, except that the heteropairs of dots are broken down into binocularly independent noise dots. In contrast to the noise dots, the binocularly corresponding dots are called signal dots, since they provide depth signals, whether normal or reversed depth signals. Noise degrades the perception of the disk's depth, and this is measured by observers' accuracy in reporting whether the central disk is in front or behind the ring. We found that the reverse depth signals by the heteropairs further degrade the perception of the disk's depth. However, this additional degradation occurs only when the viewing duration is too short for top-down feedback to take effect. When the viewing duration is long enough, there is no additional degradation. This suggests that the top-down feedback vetoes the misleading reverse depth signals from V1. Now let's look at another type of hybrid stereogram. Now the heteropairs of dots have a different disparity value from that of the homopairs of dots. In particular, their disparity values have opposite signs, so that the reverse depth signals by the heteropairs of dots agree with the normal depth signals by the homopairs of dots. As a result, the depth surface of the disk is better perceived compared to the disk in a noisy stereogram. And this is regardless of whether one views the stereogram briefly or for a longer time. This suggests that feedback can utilize imperfect feed-forward information constructively. This is perhaps similar to this perception of a white triangle. Here, image fragments suggest a white triangle in the foreground. Here, it is not clear what's suggested for the foreground by the image fragments. By combining these two images together, the white triangle is seen more vividly through our brain's image.
Is it clear? So the idea is this is kind of fragment true news. This is kind of a fake news. There could be agreeing with true news. So this is a fake news, but actually agreeing with the true news. So fake news can be constructively used to make the true news even stronger. That makes sense? So do you see this white triangle more vividly than this? Slightly more, yeah? And so you can use very little signal to see a triangle. And this very little signal is then helped by this tiny little thing to make even a little bit stronger, yeah? And so our brain is very good at doing this constructiveness, okay? When things are not very good but useful, it will use it. Huh? When things are not very good and not useful, then it doesn't use it. So it's not a linear process. It depends, and this depends is an intelligence, yeah? Part of brain's intelligence. It depends. If you're good, I'll use you. If you're not good, I don't use you. I don't let you destroy me, something like that, yeah? And so it's a very non-linear process to do this constructiveness. So, yeah.
Perception of a white triangle. Here, image fragments suggest a white triangle in the foreground. Here, it is not clear what's suggested for the foreground by the image fragments. By combining these two images together, the white triangle is seen more vividly through our brain's imagination of what a white triangle should look like. In another example, it may not be clear what is the object in this image, but once I give you a hint, now you can vividly see a duck. Top-down feedback could enable intelligent behavior in human central vision.
So therefore, in a sense that we do not know how vision works, but this, in a full picture, just like you tell me, why is the snake going that way? I don't know. Or I can tell you it's not in central vision, peripheral vision. But it looks like we are starting to have a sketch of how vision works, yeah? So this sketch comes from, let me just take this off. Comes from, there is a bottleneck. that defines kind of constrain what vision should be. And therefore it defines you have to have a looking to guide your gaze and then seeing in light of the bottleneck. And this is all motivated by the bottleneck because our brain is not big enough. Okay, and kind of standing on the traditional knowledge of the primary visual cortex, which is the biggest part of our visual cortex. Obviously, its role is not only to guide our attention, but also serves to see. And then we can connect with machine vision, and then machines can do calculus better than us, and can play chess better than us. What can you do? But machines also get food. You can show machines this image and say, oh, it's a panda. No, not bad. But you can add some texture noise, which is very, very weak to it, such that it still looks panda to us, to humans, yeah? The machine suddenly says it's gibbon. Why? It got food. So these days, most of the machine vision is feed-forward neural networks only. So maybe it's only imitating human peripheral vision. Can be easily having these illusions, yeah? And not to have illusion, central visions, people usually say, oh, machine doesn't have understanding, we human have understanding. What is understanding? Maybe the feedback, imagination is the understanding, yeah? And this imagination is, maybe we can see if the machine sees this too, I don't know. In the future, I'm sure machine will be improved. They may not only use feed-forward, the feedback will be used, but how to use it, how to build feedback networks. When networks have feedback, the mathematics and all these are very difficult. So this is the challenge facing us. Those of you who work with Ising models, and Ising model is full of feedback, and they're always frustrating, yeah? So this is the challenge to understand the brain. Okay, so that's all for today, and we have maybe only a few minutes if there's additional questions. Okay?
The difference between the right eye and left eye are for some neurons are responsive to the color, to wavelength, right? There are any neurons that can perceive the polarization, maybe, if at the left eye comes a polarization.
We humans don't have, other animals have polarization, yeah. We don't have it.
So if the difference are from the polarization,
yeah,
we can
that's why when
see
you go to movie theaters, your left eye is polarized. And we cannot tell the difference. That's why how movie theater 3D glasses works. It doesn't matter, yeah. Another thing I want to mention is machines is also different from humans in the sense that it doesn't have a bottleneck. We humans have a bottleneck, machine doesn't. Machine have all the memory, all the information, and nevertheless, it doesn't really do that much better than human, yeah? So be proud of our human brain, we are very good. We have the visual understanding, yeah? Okay. The other?
Sorry, it's related about the course, but not about this. Sorry, how it will be the exam? More theoretical?
Oh, yes, good. So
more
we have, tomorrow we are going to have a very short lecture combined with a longer question and answers for the exam, how to prepare. So more or less this is the end of the normal part. Tomorrow we're going to have a question and answer, maybe even some practice exam questions if we have time. We are also going to do a little bit of a reflection of the history of science for vision science, because you can see vision is lots of things we don't know. Maybe we're only in the beginning of knowing, and just trying to reflect what's next. Yeah, so that will be tomorrow. Good.
Other questions? Okay, so
Okay.
food.
Yeah, thank you. And please return the glasses. Yeah, thank you.